Assalamualaikum and hello. So today I would like to share about a topic that is included in lecture 5. It's about fluid in motion and Bernoulli equation. So these are the contents of the lecture. So I will derive the Euler equation and also the Bernoulli equation, and I will also explain on the uses and limitation of Bernoulli equation, and I will also explain some of the concepts that are not on the slide, which are the statics and stagnation pressure, and I also will explain on the real fluid effects. And last but not least is the examples. I will do some of the examples of the application of Bernoulli equation. So fluid motions are governed by three conservation laws, which are the mass, momentum, and energy conservation laws. So previously, you have learned that pressure varies with respect to depth. Eh? So when elevation or depth is decreased, so pressure increases. So that is for fluid statics. So starting from this lecture onwards, the fluid is now flowing or moving. So this fluid motion will lead to pressure variations as well. So why it is important for you to learn this? It's because so you can find these pressure variations in many applications. For example, in the force structure interaction. So in mechanical engineering, normally it's in hydraulic turbo machines, where, for example, you need to determine whether cavitation occurs or not. And for example, if you want to do the aerodynamics analysis and you want to calculate the lift and drag force, and in medical field, for example, you want to measure the blood pressure, and in the meteorological, for example, you want to predict the cyclonic storms, whether it occurs or not and whatnot lah. Alright. Okay. So when you want to analyze the fluid flow, you need to use some equations. So one of the equations that can be used is the Euler equation. From Euler equation, basically you can also it can also be integrated to obtain another equation which is called as Bernoulli equation. So Bernoulli, the Euler equation, it is shown on the slide here. This is the two-dimensional form of the Euler equations of motion. So how do I get this equation? I can show you the derivation. So please consider a fluid particle that has a cylindrical shape. Okay. So this fluid particle is inclined at an angle of alpha, and it is directed to L direction. So on this side we have pressure force. So this pressure force is pressure times area, where area is the cross-sectional area. And on this side we also have another pressure force. So this pressure force is also called as boundary force. So P plus delta P times A. So delta P meaning we have a change in the pressure. And we also have weight of the fluid particle going downwards. So let me show you. So this is the fluid particle. So taking the summation of force in L direction, it's equal to ma. So this is from Newton's second law of motion. So let's say this is positive. So what are the forces? P times delta A, so this is positive, minus P plus delta P, so this is negative because it's going to the other side, minus, so we take the component of the weight is equal to ma. Okay, so PA minus PA cancel, so you have delta P. So delta PA minus, okay. So weight can also be measured by using gamma times volume. So volume, if you see here, this is a cylinder, right? So it's about it's area lah, area times length. So you can replace it here. You should get gamma delta A delta L. Okay, sine alpha is delta Z divided by delta L. Okay. So, okay, mass can also be replaced with rho times volume. So, it's rho times area times length. So, you should get this as rho times A times L times acceleration. Okay. So, I will divide this equation with delta A delta L. So, I should get negative delta P delta L. So delta Z delta L, and this is rho A lah. Okay. So let the limit of delta Z approaching 0. Therefore, this should be delta. So put this together. P plus, we put a bracket, is a plus gamma Z divided by delta L. Okay, so you should get this as rho L. So this equation is called as Euler's equation. Okay. Let's go back to the slide. Okay. So note that if acceleration is 0, the equation is reduced back to the hydrostatic equation. Remember hydrostatic equation? I derived the I've shown you the derivation of the hydrostatic equation in lecture 3, where at the end you got the piezometric pressure and piezometric head equations. But in that equation, this is 0. So since this is a moving fluid or a flowing fluid, so this become rho A. Alright. So the Euler equation can be integrated along a streamline to obtain another equation called as Bernoulli equation. Okay. So if you apply the Euler equation along a streamline, okay, you see here it's streamline. So in the streamline, we normally take the tangential acceleration lah, and not the normal. So if you apply the Euler equation just now, the dl now is replaced with ds, and the acceleration in L direction just now we replace with the tangential acceleration. Okay. So tangential component of acceleration is given by the rate of change of the velocity with respect to space and also time. So to apply the Bernoulli equation, we have to have some assumptions. So we have to assume that the flow is steady and incompressible. Steady means, if you remember in lecture 4, steady means the parameter does not change with respect to time. And incompressible means density is constant. So steady, the parameter doesn't change with respect to time. So the dv over dt will become 0. So you only have this component. Okay. So you replace this into the equation, you will get this. So when you expand this, you should get this. So if you see on the right side and on the left side, you can put it together. Okay. So if you put it together, you should get this. pressure plus the pressure change due to elevation, and this is called as kinetic pressure. So if you integrate this equation along a streamline, you should get P plus gamma z plus rho v square over 2 equal to a constant. So this Bernoulli equation states that the sum of piezometric pressure, so these two are piezometric pressure, and kinetic pressure, this is constant along a streamline for a steady flow of an incompressible fluid. So therefore, since it is constant, if you apply to 2 points on the same streamline, you should get P1 plus gamma Z1 plus rho V1 square over 2 equals to P2 plus gamma Z2 plus rho V2 square over 2. Okay, so please remember this equation. Okay, so Bernoulli equations, I will explain this later. Okay. Okay, the application of Bernoulli equation, there are many applications. So one of the application is on the stagnation tube, in the stagnation tube. So stagnation tube consists of a tube that is inserted in the flowing fluid. Okay. So this tube, if you see here, okay, at the flow is very fast here. So suddenly you have a very small opening or a very small area of the tube. So therefore, at the entrance of the tube, the fluid is said to be stagnant. Stagnant. Stagnant means it's not moving. So this point at the entrance of the tube is called as stagnation point. Okay, stagnation point. So at the stagnation point, the velocity becomes zero. So when velocity becomes zero, pressure becomes maximum. So the fluid is pushed into the tube by the maximum pressure up to a certain height. Okay. So if you want to calculate any of the parameters here, so you should use Bernoulli equation. Okay. So you need to apply Bernoulli equation to 2 points. So which are the points? The points are one is before the tube and one is at the entrance of the tube. Okay. So before the tube I put it as 0.1 and after the tube I put it as 0.2. So if I can write, let me write this one as the equation. Okay, if I can write, just now you have a 0.1 and 0.2, right? So you apply Bernoulli equation to 0.1 and 2. So 0.1 is before the tube. So P1 plus gamma Z1, sorry, plus rho V1 square over 2 equals to P2 plus gamma Z2 plus rho V2 square over 2. So at point 2, at the entrance of the tube, velocity is 0 because it's a stagnation point. Okay. And we assume that it's on the same streamline. Okay. So Z is the same. So we cancel. Z1 equals to Z2 and V2 equals to 0. So therefore, P at if let's say you want to find the velocity, 1 over 2 equals to P2 minus P1. So P2 should be the maximum pressure. So if let's say you want to find V1, so you can use this over rho P2 minus P1 square root. Okay. So P2, if you know the value, and P1, if you know the value, you can calculate lah V1. Okay. You go back. So if you know P2, where P equals to rho GH, or rho GD plus L, and if you know this P1, so you can actually get lah the V1. Alright. So another application of Bernoulli equation is in pitot tube. So this pitot tube is uh, quite similar to the stagnation tube, but in pitot tube we have two tabs. So one tab is measuring the static pressure. Another tab is used to measure. This one is used to measure static pressure, and another tab is used to measure the stagnation pressure. We still have stagnation pressure because the flow here before the tube is very fast, and suddenly you have a very small opening here. Okay, so at the entrance of the tube here is called as stagnation point. So here the flow, or the fluid that is going into this opening is called as it's measuring the static pressure lah. So the static pressure. Okay. So this tube, if you see here, we have two tabs here. So one tab here is for stagnation pressure tab. So another tab here is for static pressure tab. So these two tabs, if you connect it with a manometer, okay. So basically you can calculate lah the pressure difference, because you can see here the pressure here is more than here. So it push more. This one is higher because this is coming from the stagnation pressure tab. Okay. So similar to stagnation tube just now, we have to put 2 points in the flow. So one point we put at the stagnation point, another point we put at the entrance of the static pressure tab lah. So you apply Bernoulli equation to 1 and 2. So basically this V will be 0. Okay. So if you can calculate the difference in the pressure here by measuring the difference in height here, so rho GH, so later you can get lah the value of the parameters that you want to find. So you can see here. So later we will do the example on a pitot tube. So pitot tube is commonly used to measure speed or velocity. So you can see here, this is the pitot tube attached on the. This is the wing of the airplanes. Okay. Okay, this example. So we can do this example now. A pitot tube example. So a flow metering device consists of a stagnation probe. Basically, it uses stagnation probe, stagnation tube. At station 2, station 2. And a static pressure tab at stagnation 1. So this is stagnation point. So area 2 is half of area 1. So air with a density of 1.2 kg per meter cube flows through the duct. So water manometer is connected between the stagnation probe and the pressure tab. So and a deflection of 10 centimeters is measured. So what is the velocity at station 2? So basically, the velocity that we want to measure is not at the entrance of the tube. So if you want to measure the velocity at the entrance of the tube, it's definitely 0 lah, because it's stagnation point. So this velocity that you want to measure here is basically before the stagnation point, which is at the exit of the device. Sorry, the exit of the duct. So let's do this. Okay. So write down all the information that you have. So you have density of air, that is 1.2 kilogram per meter cube. And you also have what A2 is half of A1. That's it, right? Okay. So I will distinguish these 2 points. Okay. So this point should be point 1. So this point that we want to measure is point 2, and at the entrance is point 2s. Okay, I'll put it at the top, point 2s. So basically point 2s is the selection point lah. Okay. So apply. Okay. So we want to find V2. So how do we find V2? If I apply BE or Bernoulli equation to 1 and 2, I guess I cannot get the answer because I have too many unknowns. P1 I don't know, P2 I don't know, okay, and V1 also I don't know. Okay, so I can also use another equation, or I can actually use two equations. Then I do simultaneous equation. Then I can get the answer lah. Yeah, replace the values and I can get the answer. So let's say I use BE to 1 and 2S. Why I'm not using point 2? Because I don't know the values there. Okay. Alright. 1.2S. Okay. So P1 plus gamma Z1 plus rho V1 square over 2 equals to P2S plus gamma Z2S plus rho V2S square over 2. So which one I can cancel? So basically I can cancel V2S because it's stagnation point. So I can also cancel the Z because Z, it's on the same streamline. Okay, so what do I get here is P2S minus P1 is equals to rho V1 square over 2. Okay, so basically I cannot solve this. So I need to use another equation to solve this. Another equation that I can use is the manometer equation because below here I have manometer. So I apply manometer equation to 1 and 2s. So basically P2s equals to P1. So this is air. Air or the effect can be neglected on the pressure difference. So I will start with at this point. So this one to this point is going down. So going down, you must plus gamma of the water. The fluid is water times the deflection is 10 centimeter, convert to meter 0.1. So from here to point 2s is air, so you can neglect the effect. So therefore P2s minus P1 is basically 0.1 gamma water. So this is another equation. Okay, so I substitute point 1. Okay, I substitute 1 into 2 or 2 into 1. Okay, so therefore I should get rho V1 square over 2 is equal to 0.1 gamma water. So this rho should be rho of air. because when you apply Bernoulli equation, you apply to into the duct. So therefore, from here, I basically can get V1. So 0.2 times rho water, gamma water, rho air, and alright. So gamma water, you take 9810, rho air, you take 1.2 is given. So what will you get? So 0.2 times 9810, you divide by 1.2, then square root. So you should get this as 40.4. So basically, this is V1, but we want V2, right? So we want V2. So how do I get V2? Can I use Bernoulli equation? Can I use Bernoulli equation from 1 to 2? I still cannot use Bernoulli equation. Can I use Bernoulli equation from 2 to 2s? Still cannot. So what can I do is I have to use another equation. So by the way, this equation is not introduced yet. So it is called as continuity equation. So I apply continuity equation to 1 and 2. So what is continuity equation? So basically continuity equation, it's actually the mass conservation equation. But if you can see here, this is actually in lecture 6, but I will just introduce it now. So basically, continuity equation is equal to I put it here. Okay. In continuity equation, the flow rate of steady flow should be the same. Okay. So therefore, Q1 equals to Q2. Q is the volume flow rate. So you can see here, volume flow rate you can measure by using area times velocity. So basically, this is the continuity equation. Later, I will explain on this in lecture 6. So you apply continuity equation into this equation. So A1 V1 equals to A2 V2. So basically area, it's a duct. You can area is given the ratio here. Therefore, if you want to find V2, so basically A1 divided by A2 V1. So it's given that A2 is half of A1. So therefore, this will become 1 divided by 0.5 lah. Okay, so A1 cancel. So times V1. So V1 is 40.4. Basically, 1 divided by 0.5 is 2. So you should get the answer as 80.8 meter per second. So this should be the answer lah. Alright. So 80.8 meter per second. So on the continuity equation, I will explain this in detail in lecture 6. Alright. So clear on that. So another application of Bernoulli equation you can find in when the fluid exits from a large tank. So when this in this application, you have to put point 1 and point 2. So point 1 is on the surface of the tank. So normally at the surface of the tank, because it's a very large tank, a very large tank, at the surface of a lake, at the surface of a reservoir, dam, the velocity should be 0. So you can choose this point because you will know that velocity here is 0. So it will reduce your unknown parameters. So you choose this as point 1, and another point is any points that you want to measure lah. If you want to measure at in the pipe, so you choose any points that you want to measure. So you apply Bernoulli equation to point 1 and point 2. Okay, so you must know the some of the parameters there. So Z1 uh, minus Z2 should be the height lah, height difference. Okay. Okay, another application of Bernoulli equation is uh, in okay, the pressure variation near curved boundary. So in this application, so normally we apply it in pipe. So in the pipe, the fluid is inside the pipe, right? Okay, but here the fluid is outside. So meaning you want to measure the pressure variation at the surface of the body, for example. Okay, so there is pressure variation. So it depends on the location of the on location on the surface. So if you apply Bernoulli equation along a stream tube, for example, you have to assume that one is on the tube and another one is before. And see this not is before the tube. Okay. So normally we don't really use pressure. We don't really calculate the pressure, but instead of using pressure, we use pressure coefficient. So pressure coefficient is Cp. Okay. So if you apply the Bernoulli equation just now, Z should be the same because it's on the same streamline. So you should get this lah. So if you divide this with this, you should get this, right? Okay. Okay, if you combine this equation, with mass conservation equation, so you should get this equation, okay, and it will give you the pressure coefficient. So instead of using this, you can also use this equation, which is the velocity difference here, the ratio of velocity on the body divided by velocity before, or in the streamline. And instead of using this, you can also use the spacing, the streamline spacing, because as I've mentioned in lecture 4, the spacing of the streamline also shows the the velocity difference. If the spacing is closer, velocity will be higher. Alright. So if you can see, here, okay. So the Cp, or the pressure coefficient, is positive. It's positive on this side and also on this side. But it's negative above and below this body. So why? Because if you can see here, so when you have a streamline, so the streamline will stop here, and it will be um, uh, push lah, or it will be going to this side and this side, right? Okay, because you have an object that obstruct the streamline. So this point is called as stagnation point. Okay, so on this point the pressure will be maximum lah. So when the pressure is maximum, you minus with the pressure before, or the pressure in the streamline, you should get a positive value here. So that's why the Cp is positive. But then here, the pressure will be decreased. On this side. So when it is decreasing, it become less than the pressure on the streamline. So that's why less pressure, you minus with P naught or P on the streamline, you get a negative value. Alright. So this is an example. I'm not going to do this example. If you want to know this in detail, later we discuss in class lah. Alright. Okay. So the limitations of Bernoulli equation. So this is the limitation, meaning that when you want to apply Bernoulli equation, you have to assume, you have to have some assumptions. So there are 6 assumptions. One is incompressible flow, meaning that the density should be constant. Another one is steady flow, because when you derive the Bernoulli equation, remember that the dV over dt is 0. And it has to be irrotational. So irrotational meaning it's not in rotation. There are some cases where the flow become rotational. So that one you cannot use Bernoulli equation lah. And it has to be in viscid fluid. So in viscid fluid meaning no viscosity. That's why you can have the velocity, you can have slip at the boundary. Velocity is constant. And no heat transfer, no work transfer. If there is a heat and work transfer, then you have to use other equation, which is the energy equation. Okay. So this is the last subtopic, which is the real fluid effects. So in real fluid, the fluid at the boundary will have zero velocity. So this is called as no slip condition. We have learned before. So when this happens, boundary layer will be developed very close to the body. So you can see here. So you can see the body, there's a body here. So pressure will be varied, right? So pressure varied until here you see the 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 pressure here, or the boundary the velocity profile here, it become two side. Okay? There's one side here, there's another side here. Okay? But before that, it start to separate before that, which is at this point. So this point is called as separation point. So if the mainstream is accelerating, so pressure decreasing, or if you have a negative pressure gradient, boundary layer will remain thin. If the mainstream is decelerating, pressure increasing, or adverse pressure gradient, boundary layer will separate. So meaning at this point, at this point, velocity is accelerating. So that's why the boundary layer is separated. Okay. Hence, on the front part streamlines are similar to ideal. So here is similar to ideal. However, downstream, downstream meaning after the obstruction here. So here is the separation point. So separation start to occur. So when separation starts to occur, you will no longer see the similar ideal streamline here. You can only see some disturbance here. So this disturbance, this is called as wake, W-A-K-E, wake. So separation starts to occur at Reynolds number of 50. So the higher the Reynolds number, then the higher lah the separation or the wake will be produced. So see here the wake, there are too many wake here. So this is the example for different shape. This is square rod, this is a disc, and this is a orifice. Alright. So all these are wakes. So this is for real fluid. But for ideal fluid, you will not see this. This is for real fluid. Okay. So that's the end of lecture 5. So I know it's very lengthy, but I hope that if you can get something from this slide, from this video. If you have any question, you can ask in the Telegram, or also ask in the just write the comments on the below the video. So see you guys. Thank you for listening.